Well, thanks for joining me. We're going to be discussing particles in the atom. This diagram represents a model of an atom that you're probably somewhat familiar with. Obviously, the center of the atom is the nucleus. It's composed of both protons and neutrons. Then outside of the nucleus, in these rings, these little dots represent electrons. And the atom is mostly empty space. Now, this is a rather old model of the atom, but it still is the one that most people think of as the atom. Now, we want to spend some time talking about protons, neutrons, and electrons, and how to calculate average atomic mass, and maybe what's the difference between an ion and an isotope. And that's what we're going to do now. So you should know the main parts of the atom, the different particles in the atom. Inside the nucleus, the center, are protons and neutrons. Now, protons have a positive charge. A lot of students think neutrons have a neutral charge, but neutral means an equal amount of positive and negative. So neutrons do not have a neutral charge. Neutrons have no electric charge. Both protons and neutrons have a mass of 1 atomic mass unit, or 1 AMU. An electron is located outside of the nucleus, and it has, if I say no mass, what I really mean is very, very little mass. I'll give you an example. If you drive a 2-ton pickup truck and go mudding, driving through the mud, and you get mud all over your pickup truck, it still weighs 2 tons. You don't say it weighs more because it has a little dirt on it. It's like getting a haircut and saying, look, I lost some weight. No, you lost some hair, right? So in terms of the mass, we're going to say no mass, but understand it's very, very small mass in comparison to the entire atom. Okay? So it says on the bottom, each element is chemically unique. To understand why they're unique, you need to understand the structure of the atom, the characteristics of these components. So we're going to learn to count protons, neutrons, and electrons for atoms. Now, it wasn't until 1932 that James Chadwick, pictured here, discovered the neutron. Now, protons and electrons were easier to find because they had an electric charge, but neutrons had no electric charge, so it wasn't as easy to add up to find, right? So, if you remember, Rutherford was bombarding gold foil with alpha particles, and so I'm sure Chadwick was trying to do some similar type stuff. So he took some beryllium and bombarded it with alpha particles, right? Those helium nucleus. So we're only looking at now the nucleus of the atoms, okay? So let's see if we can figure this out. Over here is this beryllium 9-4. The 9, that number there, the bigger of the two numbers, larger, is the mass. And remember, protons and neutrons have a mass. And then this smaller number, the 4, tells you the number of protons. It gives you the identity of the atom. And because here I see 1, 2, 3, 4 white circles, those must be the protons. 1, 2, 3, 4, 5 orange, those must be the neutrons. So the 4 plus 5 is the 9. So here we have 2 protons shown in white and 2 neutrons shown in orange to make 4. Now, when these 2 nuclei are smashed together, what Chadwick found was he formed carbon-12. So it had 6 protons, and you can see those white ones, 1, 2, 3, 4, 5, 6 protons, and 1, 2, 3, 4, 5, 6 neutrons, so carbon-12. Now, this doesn't add up, right? The bottom numbers, 4 plus 2, do indeed equal 6, but the top numbers, 9 plus 4, equal 13, and this is 12, and that can't be. So Chadwick figured out there must be another particle. That other particle is a neutron. It has no protons, but it does have a mass of 1, and it was in this experiment that he determined and found the neutrons must exist. Alright, let's try a little bit of humor here. 2 atoms are walking down the street, and whoops, let's start over again. One atom says to the other, hey, I think I lost an electron. The other says, are you sure? Yes, I'm positive. You can laugh if you want. If not, that's okay. Let's try another one. A neutron walks into a restaurant and orders a couple of drinks. As she's about to leave, she asks the waiter for how much she owes. The waiter replies, "For you, no charge." Ha! See, because neutrons have no charge. All right, so let's keep moving here. The symbol for an electron will go with an E. You can put a little negative there, implying it has a negative charge. Proton, we'll put a little P with a plus sign because it has a positive charge. And a neutron, we'll put an N with a naught, no charge there. So a charge of -1 for an electron, +1 for a proton, and a neutron has no charge. Relative mass, we're going to put here protons and neutrons are 1 AMU, and an electron is about 1/1840th of an AMU. Now, that's approximately the year of the Alamo. You're supposed to remember the Alamo. I think it was 1842, 1843. So 1/1840th is the mass. You don't need to actually know that number for me. If you say no mass, you're okay, as long as you understand it has a very small mass. The actual masses are given here. These will not be important for us at this point. When we move on to mass defect, then we'll revisit those values. But for right now, if you just want to know the masses of protons and neutrons are 1 AMU and electrons are no mass, we'll be fine. So here's a little graphic organizer. An atom has a nucleus composed of protons that have a positive charge and neutrons that have, notice this person per neutral charge. We know that's not right. It should say no charge, okay? But I'm not going to make fun of the person any further than that. The other part of the atom, if it's not the nucleus, are the electrons, and they have a negative charge. Most of the atom's mass is, of course, in the nucleus, because that's where the protons and neutrons reside. The atomic number is always the number of protons, and the protons and electrons, the number of those, are always equal if the atom is neutral, meaning it has no overall charge. There are smaller particles in protons, neutrons, and electrons called quarks that are found in the nucleus of the atom. I won't ask you anything about quarks in this class. All right, in terms of the size of the atom, we know atoms are really, really tiny. Now, you can actually see atoms, right? And you don't even need special glasses. If you can see something, you're seeing atoms. Now, if you mean, can you see individual atoms? Well, you can't, but scientists have now been able to actually photograph individual atoms, which I think is pretty cool. How small are those? Well, they're incredibly tiny. They measure in the order of picometers, 10 to the -12th meters. So, for instance, the hydrogen atom is has a radius of about 32 picometers. Now, the nucleus, relative to that, would be closer to 10 to the -15th meters. Okay, so like 1,000 times smaller than that, right? And there's the density of the nucleus, so it's actually quite dense, 10 to the 14th grams per cubic centimeter. So that's actually incredibly dense if you were to do the math on that. If the atom were the size of, like, let's say a football stadium, the nucleus would be the size of maybe, let's say, a marble. And so between the marble and the outer edges of that atom, there's just empty space. At least that's what Rutherford told us in his model of the atom. So there's your football stadium, and if the nucleus were there, it'd just be a tiny little marble placed in the center. All right, so let's figure out how to write chemical symbols the proper way and figure out how many protons, neutrons, or electrons. Generally in class, this is an activity that students excel at. They kind of like it, and I think they like it because they get it. It makes sense the first time. So when we look at an elemental symbol on the periodic table, it'll be written there, and then you'll have a mass number and an atomic number. Now, the color, if it's written in red or blue, doesn't matter. The mass number can be written on the bottom or the top or the right or the left. So how are we supposed to know which is which? Well, it turns out that always the atomic number is the number of protons, and that will be a whole number. It will never be a decimal. It will also be the smaller of the two numbers because the mass number is equal to protons plus neutrons, so it has to be a larger number than the atomic number. The mass number, depending on if they figure in the average atomic mass of the isotopes, could be a decimal, or it could be a whole number. More on that later. So let's look at this element here. This is the element fluorine. Now, fluorine as a molecule is F2, but as an atom, it's F. Fluorine, it would be used most commonly in a cooking pan. A non-stick cooking pan has Teflon. The F in Teflon refers to fluorine. Fluorine, if you heat up that pan and don't put oil on it, it starts to smoke, it's going to start to emit fluorine gas, which is actually quite deadly. So if a pan overheats and you don't put oil in it, it starts to smoke, one of those Teflon pans, you want to open your windows and take that pan and just chuck it out in your yard so you're not breathing that fluorine gas. And then probably throw the pan away and buy a new one. Alright, so if I were to tell you to find the number of protons, neutrons, electrons, atomic number, and mass number for this block, I think we could do it. Remember, the number of protons is always the smaller of the number, so that tells you that this thing must have 9 protons. Now this top number is protons plus neutrons, so if you would go simply 19 minus 9, you'd get 10. So it has 10 neutrons. Now, there is no positive or negative charge on this atom, so we said that the protons and electrons are equal, so it must have 9 electrons and 9 protons. Now, we don't get that from looking at the numbers. We get it from the fact there's no positive or negative charge on this. The atomic number is equal to the number of protons, so that would be 9, and the mass number is this number right here, the larger of the two numbers, 19. Okay, let's try another one. Here's bromine. Bromine's another diatomic molecule. Excuse me. But as an atom, it's Br. So, same set of questions. Number of protons, neutrons, electrons. Well, protons is always the smaller of the two, 35. Neutrons, is that 80? Not so quick, it's not 80. You got it. You got to say 80 minus 35, 45 neutrons. There is no charge on this atom, so protons with their positive charge, electrons with their negative charge have to be equivalent to have no charge, or be neutral. So it has 35 electrons. The atomic number is always equal to the number of protons, 35, and the mass number is protons plus neutrons. This is the mass, because they both weigh 1 AMU, so 80 AMU. Alright, let's try some more. Hopefully this is starting to make some sense. Here's an atom of sodium. Alright, sodium is that metal that has to be stored in oil. If you actually put it in water, it'll explode. So here's the symbol for sodium, Na. And it has a symbol because in Egyptian times, when they would embalm bodies, they would use sand that had baking soda mixed in it. And they called that substance natrum. And that's where the Na comes from sodium. Baking soda is sodium bicarbonate. So that's where the Na historically comes from. Well, how many protons? Well, the smaller number is always protons, so 11. How many neutrons? Well, 23 minus 11 is 12. Number of electrons? Well, I don't see a charge here. So if I have 11 positives, 12 things with no charge, that's 11 positive charges. And to make it have no charge or neutral overall, I must have to have 11 electrons. 11 negatives, 11 positives makes it neutral. The atomic number of this is 11, and the mass number is 23. Now let's change it up a little bit. So right now this is an atom of sodium, and now look at it now has a positive charge. So now it's an ion, a charged particle. Now it turns out it does not have 12 protons. Even though protons have a positive charge, atoms do not gain or lose protons. They're buried deep in the nucleus. The only thing that an atom can do is gain or lose an electron. And if you lose a negative charge, you become more positive. So because it's sodium, atom or ion doesn't matter, it has 11 protons. That determines, and that exclusively determines, the identity of the element. In terms of neutrons, well, electrons don't have a mass, so I don't have to worry about that in terms of anything. I just go 23 minus 11, it still has 12 neutrons to have that mass. So here's the tricky part. How many electrons? Well, if it had 11 electrons, it would be neutral. If it has 12 electrons, it would have a -1 charge. So it must have 10 electrons. 10 negative charges, 11 positive charges gives me a +1 charge. The atomic number is still 11 for sodium, and its mass is still 23. Recall we said electrons don't have a mass, so they're not going to, if you add or remove electrons, change the mass at all. All right, let's try some more. Hopefully this is all making sense. Let's switch it up a little bit. If an element has an atomic number of 23 and a mass number of 51, I want to fill in some details. So how many protons? Well, atomic number is protons, so it must be 23. How many neutrons? Well, the mass is 51, and the mass is proton plus neutron, so if I said 51 minus 23, I get 28, so it has 28 neutrons. Now, we're told here that, well, we're not told that it has any kind of charge, so let's assume that it is neutral. So if it has 23 protons, it has 23 electrons. Now, we would need a periodic table at this point, but the complete symbol for this would be vanadium. Vanadium has 23 protons, and this particular isotope has a mass of 51. Oftentimes, vanadium is added to steel to harden it. So you can imagine if you're using a box wrench up here, and you're wrenching down, pulling really hard on a bolt that's stuck, you don't want the steel in the wrench to rip or bend. So it has to be very hard. So they'll add vanadium to steel to make it harder. So this is actually chrome vanadium steel wrenches here. Okay. All right, let's try another one. An element has 60 protons and 84 neutrons, and we want to fill in the chart. Atomic number is always equal to the number of protons, 60. Mass number is protons plus neutrons, so 60 plus 84 is 144. If it's an atom, it will be neutral. If it has 60 protons, it will have 60 electrons. So looking at the periodic table, trying to figure out what element has an atomic number of 60, well, neodymium. Neodymium has an atomic number of 60, and our particular isotope has a mass of 144. Neodymium is an incredibly powerful magnet. So I'm showing a small neodymium magnet holding on to all these paper clips passing through this person's hand. Okay, if we were in person, I would do that as a demonstration for you. The neodymium magnets are what's in Bose speakers, those really small, powerful, expensive speakers that have such nice sound to them. Okay, I will tell you this, you would never want to take a neodymium magnet, or any magnet for that matter, and hold it near an external drive, because that's a way to erase it, because those images and those files are stored magnetically on there. So keep really powerful magnets away from zip drives and external drives and thumb drives and so on. All right, let's try another one. If a neutral atom of an element has 78 electrons and 117 neutrons, we want to figure this stuff out. Well, if it's neutral, that means the number of protons and electrons are the same. So it must have 78 protons, and remember, protons are the atomic number. So it must have 78 for the atomic number. Now, mass is protons plus neutrons, So if I add neutrons, 117 plus the 78 protons, I'll get 195 for the mass. We've already established it has 78 protons. So looking at the periodic table, I find what element has 78 protons, and it comes out to be platinum. And if I were filling in my block on the periodic table, I'd write 19578 PT. Platinum, in case you were wondering, is more valuable than gold, right? If you sell 100,000 records, they say you've gone gold. If you sell 1 million records, you've gone platinum. 2 million, double platinum, and so on. All right. Hopefully that all makes sense, and you can see that I can ask protons, neutrons, electrons in lots of different ways, and I will on your test. Okay? Now, let's talk a little bit about that mass on the periodic table. I said sometimes it's a whole number, sometimes it's a decimal. Now, if it's a whole number, they're simply taking the most common isotope and putting that number up there. So we need to talk about mass number and isotopes, and make sure you know the difference between an isotope and an ion, and relative and average atomic mass. And that's what we're going to talk about now. Okay? So I've cut out some blocks of the periodic table. Notice the red and blue numbers have switched locations, but that's not going to bother us, is it? Because we know the smaller of the two numbers is the atomic number and the number of protons. So for calcium, the atomic number would be 20. If I were to look, the mass number would be 40. Now remember, you can only get protons and neutrons. You don't get parts of protons and neutrons. So a mass number is always a whole number, okay, if you're looking at a specific atom. More on that later. Number of protons, well, it would be 20, the equivalent to the atomic number. Number of neutrons, well, protons plus neutrons equal 40, so it'd be 20. And because I don't see a charge, it's a neutral atom, it must have 20 protons and 20 electrons. For argon, it has an atomic number of 18. It has a mass number, well, I'm going to call that 40. Okay? Now, how many protons? Well, protons, our atomic number is 18. How many neutrons? 22, because we know that protons plus neutrons equal the mass. How many electrons? Well, it's a neutral atom, so if I have 18 protons, I have 18 electrons. Let's try the last one, bromine. Atomic number, 35. Mass number, well, I would go 80. I would round that up to 80. So number of protons is equal to the atomic number, 35. Neutrons, 35 plus something equals 80. That something is a 45. And because I see no charge, if it has 35 protons, it has 35 electrons. Okay, let's keep moving. In the Bohr-Rutherford diagram, right, we put electrons in a filling order. And maybe you remember this from junior high. The first ring got 2 electrons, the second ring got 8 electrons, and then 8 and 2. There was a particular filling order. Okay, so let's look at this. Here's helium, and it has 2 protons, and it has a mass of 4, so it has 2 neutrons. So in the nucleus, I have 2 protons and 2 neutrons. So this represents the nucleus. Now, if it's an atom, if it has 2 protons, it has 2 electrons. So in the first ring, it's going to have 2 electrons. I put the first one here. Now, do you think the second one's going to be right next to it? Or maybe on the opposite side? And of course it'll be on the opposite side. And why? If you said because electrons repel one another because they both have a negative charge, I would fully agree with you. So there's our Bohr model combined with the Rutherford model of a helium atom, a helium-4-2. Okay, let's try lithium. Lithium is atomic number 3, and it has a mass of 7. So in the nucleus, I'm going to go ahead and put 3 protons because its atomic number is 3, and I'm going to give it 4 neutrons because it has a mass of 7. In the first energy level, I'm going to put 2 electrons because that's what it says for the order. Now, because it has 3 protons, it also has 3 electrons. The first energy level is full after 2. So it's kind of like if you're trying to drive your car into a parking deck and the first parking deck level is full, well, you have to go to the next parking deck level, to the second level. And then I can put the third electron. So 1, 2, 3 there. So this is what we would consider the Bohr-Rutherford Diagram of lithium. Now, I've seen these is even in 4th grade. They're teaching this in Unit 5, which I'm not sure any of the kids actually understand it, but they put it on their little posters they put in the halls. Now, in shorthand, the way I could write this is I could put my nucleus and just put 2 electrons in the first energy level. See the first ring, 2, and then 1 in the second. So we'll use this shorthand later in the year versus drawing out all these giant circles. Now, I could have you draw some other ones, and if you want to try to take some time to do that, you'd need a periodic table to draw those out, and I'll go through those real quickly for you. Okay? If you do beryllium, it's atomic number 4, so it has 4 protons, and it has a mass of 9. So it gets 2 electrons in the first energy level, right? And then it gets 2 in the second. Well, that's only 4 electrons. Should it have 4 or 5? Well, it should only have 4 because if it has 4 protons, it wants 4 electrons to be neutral. So this is correct. If we do boron, boron has 5 protons. It has a mass of 11, so it has 6 neutrons. In the first energy level, it has 2 electrons. And then in the second energy level, it has 3 electrons. Okay? Yes, I could have moved these electrons so they weren't quite as close together, but you get, I'm just trying to show you how many are in that level. When we do aluminum, aluminum has 13 protons. It has a mass of 27, so 14 neutrons. So in the first energy level, it has 2 electrons. In the second energy level, it has 2, 4, 6, 8. So now we've used 10 electrons. We need 3 more. And in the third shell, it has 3. And so this would be the aluminum drawing. Here we have oxygen. Oxygen is atomic number 8. It has a mass of 16. So in the first energy level, right, we have to have 8 electrons. First one has 2. Second one has 6. And this is shorthand. And finally, here's sodium in shorthand. Has an atomic number of 11, a mass of 23, so 11 plus 12 is 23. We get to put 2 electrons in the first energy level, 8 in the second, that's 10, and then 1 in the third. We will do much more with these filling orders and electron configuration in our next lesson. And that's really the point of the present-day model, the orbitals, figuring out these electron configurations and how many electrons go in each orbit. All right, so let's get back to mass number. Let's delve in a little bit deeper. So I have here a drawing of what we think maybe a carbon-12 atom looks like. And if I were to look and drill down into that nucleus, I notice it has 1, 2, 3, 4, 5, 6 protons, 1, 2, 3, 4, 5, 6 neutrons. So that would be carbon-12. And of course, I haven't shown it, but it would have 6 electrons as well. So we know the mass number is always equal to protons plus neutrons. It's always a whole number because you can't get parts of protons or parts of neutrons. It's not what is on most periodic tables. Instead, they don't put the mass of a single atom, they put the average atomic mass of the different isotopes. Okay? Now I'm showing you here the 2 electrons in the first energy level, the 4 in the second, if we wanted to make that be a little more precise, a little more accurate. Okay? All right, let's keep looking. So what is an isotope? Well, atoms of the same element can have different masses. Now how can that be? Well, they have the same number of protons because of the same element, and we said electrons don't have a mass, so they must have a different number of neutrons. So isotopes have different number of neutrons. So there's the mass number, and there's the atomic number. So oftentimes we use what's called isotope notation, and we write C-12 or carbon-12, indicating that's the carbon that has a mass of 12. Now, if you were to look at these two drawings, they look identical. But if we look a little more carefully, if we look at the nucleus here, we notice that that one has 6 protons and 6 neutrons. So that's carbon-12. If we look at this one, it still has 6 protons, so it is carbon, but it has 7 neutrons if you count carefully. So that one must be, it must have 8 if we count really carefully, so that must be carbon-14. So it has 8 neutrons, 6 protons. Those would be two different what are called isotopes of carbon. The one on the left would be identified as carbon-12 or C-12, and this would be carbon-14, C-14. Now, even though they're the same element, carbon, they will have different properties because they have a different number of neutrons. So let's look at this one here. I've got, well, 3 protons. So based on 3 protons and 3 protons, that must be lithium. But on the first one, on the left, that's lithium-6. On the one on the right, that's lithium-7. Notice they have the same number of electrons, but they have a different mass. So they're different isotopes. This is lithium-6 and lithium-7. And if we were to look at these more carefully, the one on the left has 3 protons and 3 neutrons. And that's why it's lithium-6, along with 3 electrons. The one on the right, if I look carefully, has 3 protons but 4 neutrons. Those extra neutrons can sometimes make it unstable, or maybe stable, depending. And so that's lithium-7, and it has 4 neutrons and 3 protons. These are, again, examples of what are called isotopes. Isotopes have different number of neutrons. So let's try this one. I've got chlorine-37, and if I want to know the atomic number, well, the atomic number is always the smaller of the two numbers. That's 17. The mass number, well, that's this number up here, protons plus neutrons, 37. So protons and atomic number are the same, has 17 protons. Now, if it's a neutral atom, if it has 17 protons, it must have 17 negative electrons, because they have to be the same. How many neutrons? Well, protons plus neutrons equal mass, so 37 minus 17, 20 for the number of neutrons. Okay? Now, that's the isotope chlorine-37. In terms of relative mass, if you were wondering, the carbon-12 atom has a mass given here, but for simplicity, we say if you take 1/12 of the mass of a carbon-12 atom, so take this mass, divide by 12, that by definition is 1 AMU. So an atomic mass unit, don't say a mu is the sound a cow makes, an AMU is 1/12 the mass of a carbon-12 atom. That's the standard that we use today. If you're wondering what a proton and a neutron weigh, you see these are their actual masses, but that's close enough to saying a proton weighs 1 AMU, a neutron weighs 1 AMU, and an electron, well, we're just not going to worry about it. It weighs so little, it weighs nothing. Okay? Now, let's talk about this average atomic mass. It's the weighted average of all the isotopes. Okay? It's the number you find on the periodic table. Okay? And it's often rounded to 2 decimal places. That's not key, the last one. Look, if I say the average student as sophomore weighs 165 pounds, there could be students that weigh 250 pounds, and there could be students that weigh 85 pounds. That's simply an average mass. And the average is what you find on the periodic table. Okay? Now, when you find an average, the average atomic mass is, here's a formula, the mass of one isotope times its percent abundance plus the mass of a second isotope times its percent abundance divided by 100. And we'll go through some examples of how to calculate that. Okay? Now, if I look here, It says calculate the average atomic mass of oxygen. So we're saying that it has, in this case, 3 isotopes. Oxygen 16 is 99.76% of all the oxygen you find. Oxygen 17 is 0.20%. And then the last one, oxygen 18, is oxygen, excuse me, and then oxygen 17 is 0.04%. I didn't read my own question very carefully. All right? So you take the mass, 16, times the percent, plus the mass of the second isotope times its percent, times the mass of the third isotope times its percent, divide by 100, and you get 16.00. So if you were putting on a periodic table, you would have written the average atomic mass is 16.00. That's not a great example because it came out to be a whole number. I would have liked it to be, maybe have some decimals that were not 0. Okay. I'm going to skip this one and let's go into some more detail. So let's look at chlorine, for instance. So if I look at its spectrograph, if I do what's called a mass spectrogram for this, it's going to come out with 2 peaks. Now in the olden days, if this were a graph paper, you literally would have cut out the shape of that peak, and weighed the paper to determine its percent. Nowadays, a computer gives us an exact percent. The fact that we see 2 blips means that there must be 2 isotopes. So the first isotope is going to be what I'm going to call chlorine 35. It actually has a mass of 34.97 AMU, and it makes up 75.53%. So see the 75.53%. The second isotope down here is what I'm going to call chlorine 37. Its actual mass is 36.97, and its percent abundance about 24.47%. So chlorine 35, chlorine 37. If I'm looking for how to put that number on the periodic table, here's how I'm going to figure that out. Average atomic mass is equal to the mass times the percent abundance. Now, I prefer to put the percent as a decimal, and then I don't have to divide by 100 when I'm done. So I took 34.97 times 0.7553. Add that to the second mass, 36.97, times its percent abundance, 0.2447. So when you do the math, I'm keeping all these decimals in my calculation here, and you add that up, and I would get an average atomic mass of chlorine to be 35.4594 AMU. So if it were my periodic table based on this data, I would write chlorine 37 and I'd write 35.4594. And if you look at the periodic table on your chart, it's going to be very, very close to that number. What is the chance that you could find sometime in your life a single atom of chlorine that would weigh 35.4594? Well, 0. It doesn't exist. It does not exist. It's an average mass. It either weighs this amount or this amount, but not the amount that is the average. So that's the difference to when we say an atomic mass versus an average atomic mass. Okay? The average doesn't exist. But because in nature you find a sampling of all the isotopes, when we do calculations, we use the average atomic mass. How do they get that? Well, if you're wondering, I mentioned they use an instrument called a mass spectrophotometer. So electrons have a charge, so they take and they inject a source of electrons, the sample, into the machine where they're heated up, they're ripped apart, turned to a gas, and those electrons go through a magnetic field. So those streams of ions go through, and it turns out that the heaviest ions have the most mass, and they stay in the magnetic field longest, and this is called a time-of-flight detector, and they go pretty far. And the lightest ones go the shortest distance. So this work was done way back in 1919. This person won the Nobel Prize in Chemistry for figuring out how to weigh atoms using the mass spectrograph. So in very simplistic terms, you inject in here your particles, you heat them up, and they're separated by this large beam here, this large magnetic source. Now, they hit this photographic plate, and depending on where they hit, they're going to make either a dark spot or a less dark spot. The darker they are, the higher the abundance. That means more of them hit there. So for this particular sample, I have 1, 2, 3, 4, 5, 6, 7 isotopes of mercury. Now, I'm going to take this little photo here, and I'm going to put this on down here, relative number. So you're going to have a whole bunch here, not a lot of 196, a lot more 198. There's 199, 200, 201, 202. See how that's the darkest one? That means you have the most abundance. This one's the lightest, you have the fewest. And then we have 204. So these are all the percent abundances. So I've got those on my chart. Okay? So this one's 0.16%, this one's 23%, 13%, and so on. Okay, so I get all those numbers. Now, if I wanted to, I could take all of those values and I could say, what is the average atomic mass? Well, it's the percent abundance times the mass, plus the percent times the mass. So I'm going to show the work here, not that I'm going to ever give you one this complicated to do. I took the mass, 196, times the percent abundance. Remember, you have to move the decimal over 2 places. For the second one, I took the mass, 198, times 10.02 as a decimal is 0.1002, and I did that for each one of these. Then I multiplied them, added them all up. I would have gotten a mass of 200.63956 AMU based on my data. Now, on the periodic table, it says 200.59. Clearly, they're not using some of these isotopes in their calculation. Okay? They may not be as common. All right, let's try this one. It says separation of isotopes. So uranium has an average atomic mass of 238.029. Now, uranium is used in lots of things like, well, nuclear power, nuclear weapons. And you don't necessarily want the uranium-238. You might really want the uranium-235. So you might have to separate those two out. Now, if I were looking at this to find the average mass, I would take the mass of uranium, the 238, times its decimal percent, 99.3 is 0.993, add that to the uranium that weighs 235, times its decimal, 0.7%, you'd multiply by 0.007, and then you add those two fractions up, and you get a mass of 237.979. Okay? So if I were to write that on my periodic table, I might round that to 238, and that's maybe what you see on the periodic table. It says here isotopes are chemically identical because they have the same electronic structure. They cannot be separated by chemistry. So instead you have to use some other technique. Okay? So an ultracentrifuge works pretty well for that. Okay? All right, let's try some more here. Hopefully this is making a little bit of sense to you. Assume you have only 2 chlorine atoms. One atom has a mass of 35. The other has a mass of 36. What's the average mass? Well, that one you can do in your head, can't you? How about 35.5? It's halfway between 35 and 36. Now, looking at the approximate mass on the periodic table, 35.453, give me a ballpark percent. If there's only 2 isotopes, which is more common, chlorine 35 or 36? All right, 35 would be less common or more. Notice the number is getting smaller, so there must be a little bit more chlorine 35. Now maybe you're going to say, oh, it's probably 45% chlorine 35 and 55% chlorine 36. That's a good guess. Let's go with 55 and 45 and see what that would work out to be. If we made that our guess, we would take, to calculate the average, the percent abundance of isotope A 55%, 0.55 times the mass of 35. So I'm going to do 0.55 times the mass of 35. And add that to the percent abundance of isotope 2. 45% as a decimal is 0.45 times the mass, 36. Multiply those two fractions, add them up, and look at the number you got, 35.45. So you guessed incredibly close to get that mass of 35.453. You should give yourself a pat on the back because that was pretty impressive. All right, so when Dalton came up with his idea of the model, he was, quite frankly, wrong in terms of he did not talk about isotopes. Didn't make his particular idea completely worthless. It just, he didn't know of protons, neutrons, electrons, so there's no way he could know of isotopes. So he said atoms of the same element would be exactly the same, but we know they could have different number of neutrons, and that would give them a different mass. We call those isotopes. And when they have different masses, they can have different physical properties, like some can be radioactive and others are not. So if we look at things like carbon-12 versus carbon-14, we talked about radioactive carbon dating maybe in your biology class, or uranium-235 we can make atomic weapons with, but uranium-238 can't. It won't work. Okay, so clearly the isotopes matter. Let's see if we can fill in this little chart here. Okay, so you can try to pause the video, but then you can check after here. If it has 8 protons, now you're going to need a periodic table to look at this. That's always going to be oxygen. Okay, and I wrote a few things down at the bottom. Atomic number equals number of protons. Number of protons plus neutrons equal the mass. And if the atom is neutral, we would call it an atom. It has no charge. Protons equal electrons. If it's an ion, specifically a cation, cations have positively charged. It would have more protons than electrons. And if it's an anion, it would have a negative charge, and it would have more electrons than protons. All right. So this first example, if we were to look, well, I'll give you a chance to do it, and then I'm just going to click through. Oxygen has 8 protons. It has a symbol O. Its atomic number would be 8 because it has 8 protons, and has a mass of 16. Protons plus neutrons are 16. Because it has 8 protons and 8 electrons, it has no charge. Hopefully you got that one right. Let's try the next one. Potassium, if I had a periodic table in front of me, I know has a symbol K, and it has an atomic number of 19. Now, I have to be a little careful. It says it has a +1 charge. Now, I remember that protons don't change, so it still would have 19 protons. And electrons, neutrons don't have a charge at all, so that won't matter. So 39 minus 19, it would have 20 neutrons. Electrons are where it's going to matter. If I have 19 positives and I end with a +1 charge, I must have 18 negative electrons to make this work. Hopefully you got that one right. Next, Br's bromine. Looking at a periodic table, it has an atomic number of 35. That would mean it has 35 protons, and protons plus neutrons, 35 plus 45, gives me a mass of 80. Already mentioned the 35 protons. Now I have to be careful. If I have 35 protons and a -1 charge, I must have 36 electrons to give it a negative charge. 36 negative, 35 positive gives me a -1. Next one. If I have an atomic number of 30, that could only be zinc, symbol Zn. If it has an atomic number of 30, it has 30 protons. Neutrons, remember, are protons plus neutrons are mass. Did I do the mass correct? I don't think so, because I think I got these two switched, didn't I? The mass should be 65, and the neutrons, excuse me, should be 35. So those need to be switched. All right, my slide, they're incorrect. Now the charge, it's going to be a little confusing, but if I have 30 protons and 30 electrons, that's going to be a 0. So please make sure you switch the mass number and neutrons on your sheet. All right. I think we'll go through just one or two more examples, and then we'll stop. I think this video is getting a little bit long here. So if we look at atomic mass and look at oxygen, there's different oxygen atoms, and they have different percent abundances. So you'd have to average them to figure out what's going on here. Now, I mentioned that the standard atomic mass unit is 1/12 the mass of a carbon-12 atom. So if I look at, here's a carbon-12 atom, and if I break it into 12 equal pieces, 1/12 of that is what an AMU is equivalent to. I'm showing you in general, just like all atoms have isotopes. So hydrogen is 99.985% hydrogen 1, and it has a little bit of hydrogen 2 and even a little bit of hydrogen 3. But on average, hydrogen weighs 1 because that is the most common isotope. Carbon-12, there's carbon-12, carbon-13, carbon-14, but because this is such a large portion, carbon has an average atomic mass of 12.01, very close to 12. Okay? All right. Let's keep moving here. I'm skipping those, skipping that question, and maybe we'll stop here. There will be more to come on average atomic mass, so you'll get a little homework practice with that, and we'll talk more in case you have questions. Thanks for joining me and staying with me. Keep up all the hard work in chemistry. You're doing a good job.